Okay, chapter 24, mini lecture 6. We're going to look at one more set of reagents for oxidation, and that is ozone. So, ozonolysis is all about oxidative cleavage, but as you already know, we've already seen reagents that do oxidative cleavage. We've seen that permanganate can do oxidative cleavage. The key condition here is heat. Remember that if it's cold, we just get the diol, but if we heat it up, we just tear this thing apart and make the carboxylic acid, cleaving the double bond. If we use osmium tetroxide, we know that we can get the diol, but by adding a second step, sodium periodate, that periodate reacts with the diol, cleaves the double bond, and in this case, what do you get? You get the aldehyde. So to drive the point home here, I just want to make sure it's clear that the variable is that vinyl hydrogen bond. That's what gets further oxidized to give you the carboxylic acid, or not further oxidized to give you the aldehyde. So why learn another reagent? Why do we have to learn ozonolysis? Well, because ozonolysis gives us flexibility. Depending upon the workup, we can get either the aldehyde or the carboxylic acid. So how does this work? Well, as usual, start with the basics. Start with the Lewis structure. And when you look at the Lewis structure for ozone, you see some pretty normal reactivity. You see on one oxygen, I've got clearly a nucleophile, and on the other oxygen, I have clearly an electrophile. Right? Well, yeah, right, because if I have a nucleophile attack here, I can give that middle oxygen back its electrons. That's the pattern we see over and over and over again in OChem. So start with the Lewis structure, recognize the reactivity, and then do the mechanism. So here it is. We have pi electrons, and we know that they're good nucleophiles, so it makes sense that they would reach out and grab that oxygen, give that guy back its electrons, and that means, of course, that this carbon is developing a positive charge, so naturally, there you go. This guy is jumping down and making a new carbon-oxygen bond at that carbon. And that is such a mess. I'm going to do it over again with a cleaner pen. Okay, so these guys up to here, push those electrons onto the oxygen. These electrons go down and make the carbon-oxygen bond there. So that gives you this really scary intermediate. You guys know that a peroxide bond is extremely weak, and now, my God, I've got two. So this thing falls apart, and in fact, this is explosively dangerous. So, ozonolysis is a great reaction, but, slightly dangerous. No big deal. But basically, it falls apart. It falls apart quite readily, and we saw this cyclo-elimination type electron movement in the previous mini lecture. Basically, that goes down there. The oxygen gets the negative charge, and then this guy gets popped onto there. So that's how we cleave our sigma bond to get those two pieces. And what happens next, and basically you do not need to memorize this mechanism. This one's really not predictable, I'd say, but you should recognize all the electron movement arrows as somewhat sensible. So I'm going to take that funky thing on the right in the green box, and basically I just flip it upside down. And when you flip it upside down, what you're doing is you're showing that this nucleophile can happily attack that electrophile, and actually I'm not going to pop the electrons onto the oxygen. I'm going to take those pi electrons and react with that. electrophile. We are about to find out in chapter 17 that the carbonyl carbon is very electrophilic and nucleophiles love to go there. So basically we're going to clean up this mess. All right, and that all right, so we get that intermediate, and then that kind of equally explosive and dangerous intermediate. This is called the malozanide. That thing falls apart to give you your cleaved products. Here's the deal though. You've got that key vulnerable carbon-hydrogen bond that can be oxidized. You have, I hope you can see, a carbon that is in the plus -1, -1, +1, 0. Let's see, that makes this carbon in the +1 oxidation state. If I work it up with an oxidizing agent and replace that hydrogen with an oxygen, then I'm going to go all the way up to oxidation state +3. Okay, so by using an oxidizing agent, hydrogen peroxide, this guy gets further oxidized all the way up to oxidation state +3. If I don't use an oxidizing agent and I use a reducing agent like a zero-valent metal like zinc or dimethyl sulfide, that circled hydrogen, this guy right here, remains intact. It does not get further oxidized. So we end up with our aldehyde and our other aldehyde, both of which are oxidation state +1. So further oxidized up to +3, not further oxidized from this stage. And that gives us our flexibility in determining the products of ozonolysis. All right, so here's another ozonolysis example, a little bit more hairy. Oof, let's not panic. What are we focusing in on? Well, okay. I'm using ozone. This is not telling me anything about the workup. What's going on here? Look at all the functionality in your starting material and try to figure out where this is reacting. There's an ester, that doesn't do anything. There's an alcohol, that doesn't do anything. There's this funky thing we haven't even seen yet. We're going to ignore it completely. And then there is our alkene. So I'm giving you this example to show you that sometimes you actually just lose part of your molecule. The byproduct here would be formaldehyde, but that's just a one carbon piece that we don't really care about. These researchers were just trying to make this particular aldehyde from that particular alkene, and presumably they used a reducing workup. All right, that's ozonolysis. Tears it apart, puts the oxygens in. You just need to pay attention, as I said, to what's going on with that vulnerable vinyl hydrogen. And then we'll recap all this oxidation stuff, actually the whole of chapter 24 right here. The Diels-Alder, all of these reactions actually are pericyclic and concerted, meaning they happen in one swell FOUP. The orbitals have to line up. There has to be constructive overlap. You retain the stereochemistry as the reaction goes through the boat transition state, and the regiochemistry is governed by aligning the charges so that plus and minus interact, and you can figure that out from resonance. In terms of synthesis, if you see a cyclohexene, you should be thinking Diels-Alder. For these oxidations, basically the things we learned were, wow, serious oxidizing agents react with electron-rich alkenes to give syn-diols because it's one swell FOUP. It's concerted. Both of the hydroxy groups have to be on the same side. Now, I can beat up on these electron-rich alkenes or alkynes and hit them so hard that I tear them apart. I can do that with permanganate. Remember, if I do permanganate to get it to cleave, I just need to heat it up. I can do it with periodate. That goes via the diol, so I had OSO4 first to make the diol and then add periodate. Or I can use ozone, and ozone will give me either the aldehyde or the acid. So permanganate, acid, periodate, aldehyde, ozone. Flexibility is our friend. All right, and then there was the Iowan who had never been into a hotel before. So he went for his first time in his life into a hotel. He basically checked in, went up to his room, and then he called the front desk and said, "You've given me a room with no exit. How do I leave?" And the desk clerk says, that's crazy. Have you looked for the door?" And the Iowan says, "Well, sure. There's one door that leads to the bathroom, and there's a second door that goes into the closet. And there's another door I haven't tried, but it has a do not disturb sign on it." I apologize to all my Iowan friends out there. See ya in class.